Hi everyone, so welcome to this video on nonlinear classification. So far we have learned about so many algorithms, so many linear classifiers like linear SVMs, logistic regression. All of them generate a linear boundary to separate the data, right? But in many real life problems you will observe that your data is not linearly separable and still you want to have a good accuracy on a non-linearly separable data using a linear classifier, right? So the key idea that is used in machine learning is that you basically project your data into some higher dimension so that it becomes linearly separable, right? So I'm going to show you this concept, how projecting data to a higher dimension will help you to uh, uh, make make a better classification on a non-linearly separable data set like this, right? So this is a non-linearly separable data set, right? And if you make a linear boundary using some classifier, then you are not going to get good results, right? So if you directly use a linear classifier like logistic regression, you are going to do pretty bad. But we will see if we project this kind of a data set to a higher dimension where it becomes linearly separable, we would be able to do very well, right? So what is the idea? The key idea is to project, right? To take your data set to some higher dimension, right? So I will give you one example here. For example, if you have a data set of circles, right? If you have a data set containing concentric circles like this, let's say this is one circle, and you have some data points like this, right? So what you can do, you can introduce one more feature, right? And let's say this is x, and x was having two features, x1 and x2. This is x1 and x2, and in some another feature space I have, let's say, three features, and basically I'm not adding any new feature, I'm basically transforming the original features into some new dimension space. And let us say x3 is feature which is a combination of x1 and x2. Let's say x3 is nothing but x1 square plus x2 square, right? So if you see this data set now, you will see that these concentric circles are now projected along the z-axis, and the outer circle is now at some distance from the inner circle, right? So in this way, if it is in a three-dimensional case, you will be able to separate this data, right? So if, let's say, this is z-axis and this is x and this is y, you will find that these points are like this, right? And clearly if you draw a plane through them like this, you would be able to separate the data points, right? So this is what we are going to do in the code, and then we are going to measure accuracy using logistic regression on this data set as well as on this data set, right? So these two are same data sets. The only difference is we are projecting this data set into some high dimensional space, right? Okay, so let's have a look at the code, right? And yeah, so yeah, this is the dataset that we are going to generate, and after projecting into 3D, you will see that dataset looks something like this. So let's start with the coding part. Okay, so first step is to generate the data. So let's say xy equals to make circles, and let's say number of samples is 500, and let me introduce some noise, let's say 0.05, and let us print the shape x dot shape and y dot shape, right? Okay, and let us also plot these points. So plot dot scatter. Okay, so this is how the datasets look like, and let us call the show function, right? Okay, then what I need to do is I need to project this data into some higher dimensional space, right? So you can see that every example has only two features, but now I want that every example has three features, right? So what I need is I need one function which does the transformation, right? from x to, let's say, phi of x, right? So let's say x has two features, x1, x2, and phi has three features, x1, x2, and x3, right? And this x3 is nothing but x1 square plus x2 square, and this we will do for all examples, right? Okay, so this phi x is a non-linear transformation, right? Okay, so we do not know what the non-linear transformation is, but in this case we are assuming that this transformation looks like a reasonably well transformation, right? But in other data sets we would be using SVM with kernels, neural networks to do this kind of a transformation, right? So this is just for your understanding purpose, how projecting data into higher dimensions helps us to make better classifiers, right? Okay, so let us define one function phi which accepts x, the original feature vectors for all the examples. It is a matrix, right, of 500 cross 2, and this phi function applies some non-linear transformation, right? Yeah, so what I need to do here is I need to figure out what is x1, right? So let us see what is x1. So x1 is x of, for all rows, the 0th column. x2 is for all the rows the first feature, and x3 is nothing but the square of x1 plus x2, right? And let us define a new matrix, a new x. So let's say x bar, which is equal to np dot zeros, and number of samples is going to be x dot shape 0, and number of feature is going to be 3, right? And let us print the shape of x bar dot shape, and let us copy the elements from x into x bar, right? So for all the columns in x, I'm going to copy the data into the first two columns, and in the last column, in the third column, I'm going to put the third feature, which is x3, right? And return x bar, right? Okay, so let us build x bar from x. So phi of x. So you can see you're getting one matrix x bar which is of the shape 500 cross 3, and if I print the first 3 rows of x, so these are the rows, but if I print the first 3 rows of x bar, then these are like this. Sorry. Yeah, so clearly you can see the first two columns have not changed. What we did is we introduced one more column, which is basically the sum of squares of first two columns, right? So this is a nonlinear transformation we applied on our original data set, right? Now the next thing is we want to plot this data set so that we can visualize it, right? So define, let's say, plot 3D is one method which accepts a matrix x, and let us create one figure, plot dot figure, right? And maybe you can give some fixed size equal to, let's say, 10 comma 10, right? And x is equals to fig dot add subplot, projection is 3D. So this is how you can how you build 3D scatter plots in matplotlib, right? So you can refer documentation to read about these functions. So I'm basically creating only one subplot, which is a grid of 1 cross 1, and there is only one graph inside it. So this is the subplot ID, and this basically returns one axis objects which we use to make 3D scatter plots, right? So x1 is going to be the 0th feature, x2 is going to be the first feature, and x3 is going to be the third feature, right? Okay, and then you use this axis.scatter method, which takes x1, x2, x3, and then you have to specify which axis should be the z axis. So I'm taking the default axis as the z, right? So, and color is given by y, and depth shadow is one parameter, which will basically help us to add some transparency to the pixels which are at some depth, right? And then I'm going to return axis, and maybe you can call this function, and you can call plot.show, right? Yeah, so let us call this method plot3d, and let us give our new matrix, which is x prime, right? So yeah, you can see this is the graph, right? And maybe we can download the file and run it as a py file, so that we can rotate the graph as well, right? Okay, so you can see this is the graph in 2D, and this is the new graph which is in 3D, right? So clearly you can see that you have this data set, and it looks like we should be able to separate this data, right? And this is the top view of the data, right? From the top it looks something like this, and from the sides it looks something like this, which means we can draw a plane which passes through these data points. Maybe we can also try to reduce the noise so that separation becomes more clear, right? So let me just reduce the noise, right? Yeah, so instead of taking 0.05 as noise, let's say the noise is 0.02, and let me run this file again, right? Yeah, this is the data set, and this is how it looks in a three-dimensional space, right? Clearly much better, right? So if we use a logistic classifier or any other linear classifier, it would be able to separate the two classes, right? So this is the top view, and this is the side view, right? Clearly you can see you should be able to separate these two classes because the points are far apart, and you can also use linear SVM to solve this, right, using Pegasus, right? So let us go back to the notebook. And maybe we can reduce the noise here as well. Yeah, so this is the data, and we are also returning the axis object. If you need, we might use it later on, right? Then the next step is we want to figure out how well the results are using a linear classifier on it, right? So let us test for the logistic classifier on both the datasets. So let us build one logistic classifier. So from sklearn.model, from sklearn.linear model, import logistic regression, right? Okay, the next step is to create one object. So lr equals to logistic regression, and let us do some cross validation. So from sklearn.model selection, import cross validation score, and let us call cross validation score on logistic regression, where the data set is x and y, which is a two-dimensional data set. And let's say we want to do a 5 cross 5-fold cross validation, and let us get some accuracy, right? And if I print the accuracy on X data, which is a 2D data, is percentage 0.4f percentage accuracy into 100, right? So you can see you are getting around 42.4% accuracy, which is not a very great accuracy. Instead, it is a pretty bad accuracy on this data set, right? Because what your model is doing, it is generating some hyperplane like this, and this is going to give you almost around 50% of the error, right, or more than that. So this is not a good classifier. But if we use logistic classifier on our new dataset, which we have built by projecting in a 3D space, so let us see what the results are, right? So I'm just going to copy this code, and I'm using the same classifier. Instead of X, I'm going to give X bar, which is our projected data, and let us see. So you can clearly see the accuracy is 100%, right? And let us also visualize the decision surface. Okay, so our model has learned some weights. So lr.fit x bar and y. So lr dot coefficient, right? So these are the weights, and lr dot intercept will give us the bias term. So this is the bias, right? So what I need to do is I want to see where the hyperplane is, right? So in this kind of a data set, right, in this kind of a data set, we are going to get a plane, right, a plane in 3D, and this plane would have equation like this, right? If these are the data points, then there is going to be a plane ax plus by plus cz plus d equals to 0. So you can figure out that c can be written as minus of ax plus by plus d divided by, z can be written as divided by c, right? So where a, b and c are the weights, right? So a is w0, b is w1, and c is w2, right? So I'm going to compute what is the value of z. Then for x and y, I'm going to generate a mesh. I'm going to generate some data for x and y. I'm going to compute z for it, right? Okay, so let us generate some data points x comma y equals to np dot mesh grid, and here you can give some range from, let's say, -2 to 2, and range is -2 to 2, right? So let me see what is this xx yy. So you are getting two matrices. Basically, if you want to generate a surface plot, you need to generate one mesh grid, right? And for these values of x and y, I can compute the value of z, right? So z is going to be, let us also define the weights, right? So weights equal to this, bias equals to this, and if I print weights, okay, then the zeroth weight is given by w of 0, 0, w of 0, 1, w of 0, 2, right? So z is going to be minus of weights of 0, 0 into x plus weights of 0, 1 into y plus the bias term, right? Bias is given by, this is the bias term, right? And then you need to generate, you need to divide by weights of 0, 2, right? And let us print z, right? Okay, y, it should be yy, right? Okay, so z is also a matrix. Now you have three matrices, and you can make a plot, right? So let us see how we can make a plot. So first of all, let us call this function plot 3D, and we give the data x bar, and this also returns us an axis object. So I'm going to take this axis object, and where is this function, and let us not show the graph here, show equals to true, and we will show the graph only if the show value is true, right? So if show equals to true, otherwise we are just going to return the axis object, right? Oh yeah, it should be double equal to true, right? So if I'm not showing the graph, then I can draw on this graph also, right? So what I'm trying to do here is I want to draw on the same graph, right? So that is why I'm returning the axis object. Okay, so let us call this method axis dot plot underscore surface, which gets xx, yy, z, and maybe some color map if you want to specify, right? And plot dot show. Yeah, you can see there is a hyperplane, right? So we do not need to call the show function while plotting the point, so we should call this function only when you have plotted the surface also, right? So, and maybe there is some parameter to set the opacity, right? Alpha value, right? So we need to check how to give transparency, right? Let me check. So the parameter is called alpha, and let's say it is equal to 0.5, right? So yeah, you can see, right? And now again, let us download this code and try to see it in a three-dimensional space, right? So this is the original data, and this is the transformed data, and this is the hyperplane, right? You can clearly see that your logistic classifier is able to separate the two classes, and this looks like a good separation, and this is the reason you are getting 100% accuracy on this data set, right? Okay, so you're getting a 100% accuracy, right? And this is the top view, right? You can clearly see, right? So alright guys, I hope this idea of projecting the data into three-dimensional space and how increasing dimensionality helps us to how increased dimensions helps us to do a better classification. And in the next video I will talk about SVMs and kernels, and this idea is also extended to neural networks, and I hope you learned a lot from this video. Thanks for watching. See you in the next video.